Hey everyone. So in the last lecture, we talked about planar kinetics of a rigid body with force and acceleration. And in this mini lecture, we're going to do a few examples on a similar topic, planar kinetics of a rigid body, but this time with work and energy is what we're focusing on. So here's our example. So we're given a 50 kilogram wheel and it's subjected to a 50 Newton force. The radius of gyration of the wheel about its mass center O is, case of O, is 0.3 meters. And we're told to find the angular velocity of the wheel after it has rotated 10 revolutions. The wheel starts from rest and rolls without slipping. So we start out with a plan. So we're going to use the principle of work and energy here to solve the problem, since distance is the primary parameter involved. So we draw a free body diagram of the wheel, and then we're going to calculate the work of the external forces. So I've drawn the free body diagram as such. So take a few seconds to look at that. Make sure you understand the details of the free body diagram, and then we move forward. So since the wheel rolls without slipping on a horizontal surface, only the force P's horizontal component does work here. All right. So let's go ahead and go through with the solution. All right, so we're gonna take a look at work specifically. So we're gonna use U1 through 2. And for us, that's equal to integral of f dr. So that's equal to the integral p cosine 30 ds. All right, so next line, U1 to 2, and then we can go ahead and enter in 50 cosine 30, and then 10 times pi 0.8, and that gives us 1088 Newton times meter. All right, so after we look at the work, let's take a look at the kinematic relation. All right, the kinematic relation. All right, so what will that be for us? So for us, it'll be V sub O is equal to R times omega, which is 0.4 omega meters per second. And now we can look at the kinetic energy for us. Okay, so it's going to be first T sub 1 is equal to 0. T sub 2 is 0.5. Let's see, M times V sub O times 2 plus 0.5 I sub O, and this is omega squared. All right, now let's take it a little bit further, and then we'll have 0.5 times 50 times 0.4 omega squared plus 0.5, and let's see, it's times 50, 0.3 squared. All right, and then we can go ahead and then find T sub 2 to be 6.25. You can do all the work in between, 6.25 omega squared. All right, and then lastly, that takes us to work and energy. Work and energy. All right, so work and energy will be T sub 1 plus u sub 1 to 2 is equal to t sub 2. This looks very good for us. So 0 plus 1088 from above equals 6.25 omega squared from directly above. All right, and then solving for omega, you do the algebraic details in between. You get 13.2 radians per second. Okay, so with this example, we're still in the area of planar kinetics of a rigid body, but this time we're going to look at the conservation of energy. So we're given a 30-kilogram rod being released from rest when theta is 0 degrees. The spring is unstretched when theta is 0 degrees. We're asked to find the angular velocity here, angular velocity of the rod when theta is 30 degrees. All right, so the plan here is, since the distance is a parameter and all forces doing work are conservative, we use, of course, conservation of energy. So we're going to determine the potential energy and then the kinetic energy of the system at both positions, and then apply conservation of energy's equation. All right, so let's take a look back at the diagram. So here, let's put the datum in line with the rod. Let's put the datum in line with the rod. So let's draw this dotted line here. All right, so datum. And we put it in line with the rod when theta is 0 degrees. So then that means the gravitational potential energy when theta is 30 degrees is as such. V sub G2 equals negative 30 times 9.81. And then we have times 1/2, 1.5 sine 30 degrees. And then it's equaling out to a negative 110.4 nm. All right, now the elastic, let's write this out, the elastic potential energy at theta equaling 0 degrees, this is 0, since the spring is unstretched. So the elastic potential energy when theta is 0 degrees is 0, because the spring is unstretched. So the unstretched length of the spring is 0.5 meters. That's the unstretched length of the spring. The elastic potential energy at theta equaling 30 degrees will be V sub E2. So then we have 1/2 80 times this quantity here, the quantity of, we have the square root of 0.52 plus 1.5 sine 30, right, squared, minus 0.5 squared. And that's equaling out to 6.444 nm. And now we get to the kinetic energy. Right, kinetic energy. Let's clean that up a bit. All right, the kinetic energy. So the rod is released from rest at theta equals 0 degrees. So V sub G1 equals 0, and omega sub 1 equals 0. So thus the kinetic energy at position 1 is T sub 1 equals 0. All right. At 30 degrees, right? At theta being 30 degrees, the angular velocity, omega 2, and omega sub 2, I'm sorry, and the velocity at the center of mass is v sub g2. So the velocity at center of mass is v sub g2. The angular velocity is omega sub 2. All right, so the velocity at the center of mass v is v sub g2. So now we have t sub 2 is equal to 1/2 m v sub g2 squared plus 1/2 I sub g omega squared squared. So let's take a look at what we can do now. So now we have 1/2 times 30 times v sub g2 squared plus 1/2, and then we'll take it times this quantity of 1/12 times 30 times 1.5 squared, that quantity, and that'll be times omega sub 2 squared. Okay, so next we can say that since v sub g2 is equal to 0.75, sorry, let's erase this parentheses, 0.75 omega sub 2. Since that's the case, then we can go ahead with t sub 2 equals 1/2 30. And instead of the v sub g2, I can just go ahead and plug that in. 0.75 omega sub 2 squared. And then, because that's squared up there, plus the 1/2, and then I'll just rewrite some stuff. 112, 30, 1.5 squared, and this is times omega sub 2 squared. All right, and then after that, just leaving the calculations up to you, you should get t sub 2 equals 11.25, and that's omega sub 2 squared. All right, so now all terms in the conservation of energy equation have been formulated. So writing the general equation and then substituting it will yield. So let's write the general equation of conservation of energy. So that'd be T sub 1 plus V sub 1 equals T sub 2 plus V sub 2. So we have 0 on the left side. 0 plus 0 is equal to what we have from above, 11.25 omega sub 2 squared, plus that v sub 2, which is negative 110.4 plus 6.444. All right, and then go ahead and you would have to just solve for omega sub 2. All right, you take care of the algebra within this. Solving for omega sub 2, you get 3.04 radians per second.